Hello, my awesome AP Chemers. Today we're going to talk about kinetic molecular theory. So kinetic molecular theory is really big. It explains the behavior of gases and their movements. So kinetic means motion, molecular, motion of the molecules, and that theory, like I said, explains properties of gases. So kinetic molecular theory has several statements. Let's go through them. So first, gases are composed of tiny particles that have mass, with very large spaces between the particles. So this means that the size of each of the gas particles is really, really small compared to the container, and so it's negligible compared to the container. It also means that because you have large spaces between these gas particles, you are able to compress those gas particles and make them occupy a smaller volume. So key things here: gas particles are small, they have mass, and they are compressible, and their size is super tiny compared to the container, and so we can kind of ignore their volume. So we're saying that the volume of the gas particles themselves is negligible, so when we do calculations we just use the volume of the container typically. The next statement says that gas particles are moving randomly. They're moving very fast, and they're moving all the time at various speeds. So when we talk about the speed of the particles, we're talking about the average speed. So, remember that kinetic energy is related to temperature, and so when we say it's a certain temperature, we're saying this is a certain average kinetic energy, and so some particles are moving fast, some particles are moving slow. We're taking the average of them when we're relating it to temperature. Next statement says the forces of attraction or repulsion between gas particles are negligible, except when they collide. So gas particles do attract each other. Any two bodies that have mass will attract each other, or if their electron clouds touch, they repel each other, right? So gas particles normally attract each other. We call those interparticle attractions, intermolecular forces. So gas particles, of course, have intermolecular forces, but because they're so small and they're so spread out, they're so far away from each other, that attraction is negligible. The only time that attraction is not negligible is when the gas particles collide together. Then, they're in close proximity to each other, and so the intermolecular forces are significant then. But usually, gas particles are so far away, so we can kind of ignore that attraction and say that there's not really any intermolecular forces between gas particles. The next one says collisions between gas particles are elastic, so no energy is lost. We know that's not really true, but it's just so minimal that it is almost true. So, this is kind of an assumption, along with that there's no intermolecular forces, along with the volume is negligible. So all of these are kind of like assumptions that are close to reality, but they are assumptions. The gas pressure is created from collisions of the particles with the walls of the container. So when the gas particles hit the walls of the container, that's when you have pressure. And the average kinetic energy of a gas is proportional to its Kelvin temperature. So we know temperature is related to the average kinetic energy. And so if we look at the average kinetic energy here, we say that it's proportional to the temperature in Kelvin. Remember that you can remove the proportionality symbol by putting an equal and a constant. So the constant here is 3/2 R. So kinetic energy is actually equal to 3/2 R times the Kelvin temperature, and R being the ideal gas constant. You do not need to memorize this equation or anything. This is just, FYI. You do need to know that the average kinetic energy is related to the kinetic the temperature in kelvins. So based on that, if we wanted to calculate the speed of a gas, what we can do is we can say, well, we know that the kinetic energy is 3/2 R times temperature, and we also know that the average kinetic energies have mv squared, m being the mass and v being the velocity. So since both of these are equal to the kinetic energy, we can set them equal to each other, and if you solve for v here, you get this equation. This is called the mean square root velocity equation, or Rms speed equation. In the past, we used to have to use this equation. It is no longer on the equation sheet, no longer on the AP exam. The only thing you need to know here is qualitatively how does the speed relate to the temperature of a gas. And so you can see that it's a direct relationship. When you increase the temperature, you increase the speed of the gas particles. That's really all you need to know from this equation. So I have a little box here for you to remind you about that. So you will not be asked to perform calculations of root mean square speed on the AP exam anymore. But you do need to know that it is dependent upon the molar mass. The speed is inversely related to the molar mass, right? The heavier your particle is, the slower it's going to go. And also it's dependent on the temperature. So the particles at a higher temperature move faster. So qualitative, not quantitative. Okay, so know that the speed is related to the molar mass and to the temperature, direct relation to the temperature, inverse relation to the molar mass. And we're going to talk more about the relationship between the speed and the molar mass in our next video with Graham's law. So if we were to look at the speed of the particles, of gas particles, remember that when we look at the temperature, it's showing us the average kinetic energy, which means the average speed. So remember, there are particles moving fast, particles moving slow. We're just looking at the average. So we can draw a Boltzmann curve or a Maxwell-Boltzmann curve to show us what all of the particles are doing at a given temperature. So if you look at this curve here, this would be the number of molecules, and this would be the molecular speed. So at a given temperature, if I were to graph what this would look like, it would kind of look like a bell curve almost. Kind of like that. So what is this showing us? This is showing us that few particles, so this is the number of particles, and this is the speed, right? So few particles are moving very slowly. Few particles are moving very fast. The majority of the particles are kind of like average, and so if you really take that average, this is your RMS, your root mean square speed. So basically, when we look at a certain temperature, we're looking at the average kinetic energy. Again, some particles are moving slow, some particles are moving fast. Now, what if we change the temperature? So what if we increase the temperature? So I'm going to do it in a different color here, and we'll do a higher temperature. What do you think would happen? Well, at a higher temperature, the particles are going to move faster. Remember, we're looking at the average. So you will still have some particles moving slow, you'll still have some particles moving fast, but the average is going to be a faster speed, right? So it's going to shift your curve a little bit. And, I'm sorry, let me erase that part. It's also going to flatten it out a little bit more. I'm sorry, that doesn't look like a very good curve. So there's your new RMS, right? This is at a higher temperature. If I increase the temperature even more, it would look like this. And there's your new RMS. So this is, let's just, say this is, let's see, 450 Kelvin, for example, just pretending. This would be like 400 Kelvin. And maybe this one is like room temperature 298 Kelvin for the same gas. So at a higher temperature, you have more collisions, higher speed, more molecules at that higher speed, and you get your molecular speed distribution kind of like flattening it out. So this is the same gas at different temperatures. Now, what if we're at the same temperature, but we're looking at different gases? So this is a little bit of the relationship between the speed versus the molar mass, versus the other one was the relationship between speed and temperature. So if we take a look here, this is a Boltzmann curve again. This is your speed, your molecular speed, and this is the probability density, or you can think of it as number of particles again. And notice that xenon is this curve right here. This one is argon. The yellow is neon, and then the blue is helium. So these are all noble gases, and they're all at the same temperature. What do you notice? Well, helium looks to be the fastest, right? Because remember, this is the speed. So its average is probably somewhere around here. It's pretty fast. Xenon, on the other hand, is super slow. Its average is probably somewhere here, which is very, very slow. So that tells us that the heavier the gas, the slower it's going to be. And the lighter the gas, in terms of molar mass, the faster it's going to be. So this here is helium versus, I'm just going to label xenon there. Okay, so the lighter the gas, meaning lower molar mass, the faster it is.